Hello there and welcome back. Welcome back to our fourth help video over 8-20, our test premiere, the written part, part 2. This is a great review for your test. The test, of course, will look very much like this. And we're going to pick back up where we left off with question 15. We're looking at double displacement reactions. And let's take a look at what happens here. This time we're going to be reacting lithium hydroxide with sodium bromide. Where do we get the formula LiOH? Well, we learned that the hydroxide ion, a long time ago, we learned that's 1 minus. Lithium is in family Roman 1, the alkali metals. They will always become 1 plus. We crisscross a 1 and a 1, that's LiOH. Is it aqueous? Let's take a look. Here's lithium. We head over on the row, and we stop on the hydroxide column. Yes, it will be pulled apart by water. It will dissolve in water or dissociate in water into LiOH, Li plus and OH minus. Sodium bromide. Sodium is also an alkali metal. It will lose 1 valence electron. Bromide is a halogen. It wants 1 valence electron. The halogens are Roman 7. Group 17, they need 1 electron to satisfy the octet rule. So we have a 1 minus and a 1 plus. Crisscross, the formula is NaBr. Now what happens in this reaction? Well, it's double displacement. There's the Li. The Li, the first thing here, Li, will want to join with the second thing there, Br. Sodium in a double displacement or double replacement or ion exchange. Sodium is going to exchange places with the lithium. So the sodium, Na will end up with the OH. Again, they're all 1. So the LiBr, cross a 1 and a 1 minus. Sodium's 1 plus, crisscross with the OH. Let's see if they just traded places. The Na is now with the OH. There it is. The Li is now with the Br. The Li, the first thing here, ends up with the second thing there. There it is. But let's see. In order for a double displacement reaction to happen, one of 3 things must happen. We must form a gas. That's not happening in here. We must form water. That's not happening in here. Water forms when it's a acid-base neutralization reaction, which is a special category of double displacement. So will the third thing happen? Will a solid form, a precipitate from solution? So we come over to Li. Li's bumping into the Br. So we go Li over to the Br column. Nope, that stays aqueous. That would stay aqueous. We look at NaOH. Here's our Na, sodium. We go over to the OH column. It's right there. That is also aqueous. No solid precipitants will form in this reaction. That is an NR. No reaction. And it's because these are aqueous. These are both aqueous. So no precipitate will form. That's no reaction. All right. Our final question on this page. Sodium phosphate is in a solution of water. Sodium phosphate, Na3PO4, is in a solution of water. Aqueous. Let's make sure that's even possible. Here's sodium. We go over to the phosphate column, which is right here. Here's the phosphate column. Yep, sodium phosphate. It will dissolve. It will be pulled apart in water. So that means in water we're going to have phosphate ions floating around. Phosphate ions, they are 3 minus. That is where they got the Na3PO4. Sodium's a alkali metal. First family, Roman 1, they are always 1 plus. It's the only thing they can become. They have 1 valence electron. They'll always be 1 plus. 3, 1. So this is what we have floating around in solution. And they're asking which of these 3 salts right here could we put in solution, mix with the sodium phosphate to get the PO4 to precipitate out of solution. Lithium sulfide, ammonium iodide, or potassium acetate. They want to precipitate the phosphate out. So how do we know which one to look for? Well, we're going to go down the phosphate column to find out, will it form a solid precipitate with any of these metals? Remember, the phosphate ion, the second thing here, is going to join with the first thing in these salts. In a double displacement reaction, the first thing here will join with the second thing here. So let's start with potassium. That potassium, if we put that salt in solution and the K's bump into the PO4s, will they precipitate out of solution? Here's phosphate. Where's the potassium? There's potassium. We come over to the phosphate. No, they will not. They would stay in solution. This third salt will not work. This third salt will not work. The first thing here, when it bumps into the second thing there, it won't precipitate out. What about when the first thing here, the ammonium ion, bumps into the phosphate ion? Could that precipitate out of solution? First thing here, second thing there. Let's go back up to the ammonium. There's ammonium. We come over to the phosphate. That salt will not work. When the ammonium ion bumps into the phosphate ion, no precipitation will occur. What about our first one right here? What happens when the lithium ion bumps into the phosphate ion? We go up to our lithium. We come over to the side. There's the phosphate column right here. That one will form a solid precipitate. That one will work. Lithium sulfide will work. So we write lithium sulfide right here. Where did they get this? Where did they get this particular equation from? Well, we know lithium's in family 1. They are always 1 plus. Sulfide is in oxygen's family, Roman 6, group 16. They have 6 valence electrons. They need 2 more to get 8. Crisscross. That 2 comes down, that 1 comes down. This is double displacement. The lithium is going to exchange or trade places with the sodium. Lithium is going to take sodium spot. There it is. We already saw above that that's going to precipitate that phosphate from solution. Phosphate ion, as we learned long ago, is 3 minus. We already explained lithium's 1 plus crisscross. Now, what happens when the sodiums, the first thing here, ends up with the second thing here? Sodium and lithium traded places. What's going to happen there? Sulfide, as we mentioned, is 2 minus. Sodium still 1 plus, crisscross, Na2S. Will that precipitate from solution? We find lithium, we go over to the sulfide column. There's the sulfide column. That will remain in solution. It will not precipitate out. Number 16, one of my favorite questions. That is a wonderful question. We continue on to the next page. This time we're looking for activity series to decide whether reactions will happen. This is the activity series of the metals, most active at the top. Our less active metals are at the bottom. It tells us with the increase in activity as we move up. Here's our activity of the halogens or nonmetals. Iodine's least active, fluoride's most active. We continue on up. Iodine's less active than fluorine. Activity increases as we move up. All right, if you remember, metals replace metals, nonmetals replace nonmetals. In our first reaction, they're dropping a piece of magnesium in a solution of iron 3 sulfate. How do I know this is iron 3 sulfate? There's a 3 right there. They crisscrossed the 3 from iron. The 2 came from sulfate. So the question is, for this reaction to happen, magnesium would have to be more active than iron. So we look on our list. Here's iron, here's magnesium. Magnesium is above it, so magnesium's more active. That means the magnesiums will be able to force electrons onto the iron and knock it out of solution. So magnesium is going to replace iron in this equation right there. So there's the magnesium. It's an alkaline earth metal, always 2 plus, sulfate's 2 minus, crisscross. Iron was 3 plus, but they took electrons and they lost their charge and precipitated out of solution. We look, I've got 2 irons there, so I need a 2 there. I've got 3 sulfates there, so I need a 3 in front there. If I put a 3 in front there, that 3 goes there. That reaction is a single displacement reaction. The next one, we're looking at tin right here. And they're dropping a piece of tin in a solution of potassium nitrate. Where did they get this equation for potassium nitrate? If you looked at this thing, potassium nitrate, potassium is 1 plus. It's in family 1. Nitrate ion's always 1 minus, crisscross. Is tin active enough that it's going to force potassium out of solution? We come up. Here's tin, way down on the bottom, one of our least active metals at all. Here's potassium, all the way up on the top. Potassium ranks among the most active metals at all. That means it will not take electrons from tin. That's a no reaction. That's a no reaction. All right then. Now we're dealing with nonmetals. We know that nonmetals will replace nonmetals. Nonmetals will replace nonmetals in solution. So, in order for a nonmetal to replace another nonmetal, it has to be more active than it. So here they're dropping iodine into a solution of potassium chloride. We come on up to our activity list. Iodine's the least active, chloride's second most active. Iodine cannot replace, the less active iodine cannot replace chloride in solution. That's a no reaction. In our next one, we have fluorine. Why is there a 2 after the fluorine there? You will remember all the way on the front page. There's our diatomics. Our halogens, fluorine, chlorine, bromine, and iodine. Those are always diatomic. Family 7, they need to share 1 electron with each other to get 8. They'll form a single bond to end up with 8. Fluorine is at the top of the activity series for the halogens. So it definitely can replace this thing. But who does fluorine replace? Nonmetal replaces the nonmetal. So fluorine is going to replace the iodine. Where do they get this formula? Family 7, halogens, always 1 minus. Lithium, family 1, always 1 plus, crisscross. Same reason that these are 1 plus and 1 minus. Iodine's 1 minus, lithium's 1 plus, one of each of these. Who got knocked out? The iodine did. Why is there a 2 after the iodine? Right there. Brinkelhoff, it's the in Brinkelhoff. So if I've got 2 of these, I need a 2 in front. If I got a 2 in front here, that gives me 2 lithiums. I need a 2 in front there, that gives me 2 fluorides. Glad I have that 2 there. Glad I have that 2 there. We're going to stop this video right here with number 20. And we will proceed on the next video with the next page. Thanks for watching. If you have any questions that are not being answered on the help video, do not hesitate to email me. I'm glad to help.